Welcome everyone. Thank you for taking time to attend the session. My name is Rahul Bhatia. I work as a solution architect with AWS. And today we'll have Amandeep Khurana from Cloudera talk about some of the best practices and some of the lessons we learned while working with few customers on how to run optimal Hadoop on AWS cloud. With that, I will have Amandeep start and talk through the rest of the session.
Thanks, Rahul. So we'll talk about what all we've learned at Cloudera as we've supported Hadoop clusters in AWS, and I'll talk about different things from storage, compute, and just all aspects of it. A little bit about me. I'm a principal solutions architect at Cloudera, and I help our customers build solutions on top of Hadoop, as well as work with our partners on integrating with Hadoop. Before this, I was an engineer at AWS on Elastic MapReduce, and I'm also a co-author of the HBase in Action book. So we'll briefly touch upon the motivation on running Hadoop in AWS, and what we hear from our customers are common things that they sort of talk about when looking at Hadoop deployments in AWS. From there, we'll go into different deployment paradigms that we've seen, considerations around storage, networking, considerations around different instance types and how to pick which one's most optimal for your use case. Security, we'll talk about high availability backups and disaster recovery and how that looks a little different in AWS than on-prem deployments. And from there, we'll go into all the things that you want to think through when you're planning a cluster. To wrap it up, I'll talk about the available resources that you have to get you started. So, there's really two trends, and I won't spend too much time on this, given that you guys are here, you know what sort of is happening in the cloud market per se and the big data space, right? But there's really two parallel trends that we are seeing of commoditizing infrastructure with cloud and commoditizing data with all sorts of big data technologies out there, and Hadoop specifically. And as these two worlds are sort of converging for our enterprise customers, they talk about different things. They talk about cost as a motivation. They talk about just the flexibility of deployments as a motivation, ease of use, somebody else is managing their operations as something that they care about, where data is being generated and where they want to keep it, performance considerations, security. So these are all the things that come up when people look at production enterprise-grade deployments running in AWS. So, as we look at these two worlds converging, there's really traditionally what used to happen and still happens, where customers have they host their infrastructure and they manage it, and they manage their deployments on top of that, right? Oftentimes customers they outsource the management portion of it to companies like TCS, Accenture, T-Systems, and so on and so forth. And that's a very normal thing that we see in a lot of our enterprise customers. So that is where it is customer hosted but managed by somebody else. Then there is this paradigm of somebody else is hosting it, but the customers manage the deployments themselves. So they could use infrastructure from software, AWS, Google, Azure, what have you, but deploy their own software on it and manage it themselves. And then there's this whole other paradigm of just somebody else is hosting it, somebody else is managing it, they're just consuming it as a software as a service or platform as a service. And that's where you have Elastic MapReduce, Altiscale, Kubol, and the likes of those fit in that bucket. What we'll talk about today is a vendor hosted, so it's hosted in AWS, but customers managing it themselves. And that's what we see from a lot of our enterprise customers, that's what they want. So we'll talk about everything that we've learned in that bucket. And the devil's really in the details, right? So we talk about what kind of instances, whether you want fewer disks, whether you should go to S3, you want more CPU, less CPU, how much memory, and so on and so forth. And we'll sort of talk about all those things. The primary consideration, when deploying in AWS is what is your storage substrate, right? And that is what you want to look at as the first decision that you have to make. What is your storage substrate for your big data deployment, for your Hadoop deployment? And there's really two choices there, right? So there's either S3 or HDFS. So your source of truth would either be S3 or HDFS. And the way you make this decision is by looking at the kind of workloads that you want to run. So if you want to run ad hoc batch workloads, which is I've got some data living in S3, I want to run some MapReduce job to just cleanse it and make it available for querying thereafter, but it's like once I need to do it, I don't need to do it again. So it's sort of ad hoc where somebody comes in and wants to run a particular kind of job. You could do that with S3 or HDFS. So data living in either of those systems, you can very well run an ad hoc batch workload. You could do the same thing with SLAs. Say every night at midnight, I want to run this job when data becomes available, and for that day's data, I want to cleanse it and make it available for reporting down the road. Again, you could do that with S3 as well as with HDFS. But then there's this other class of workloads which is interactive, right? So ad hoc interactive workloads where people just come in and let's say BI, right? So they have a BI tool that they want to put on top of the data that's living in HDFS and do exploration of data. So that's more sort of ad hoc interactive workloads. You can't do that with S3. And S3 is really for, I won't call it archival storage, but it's not meant for interactive workloads. And with HDFS, you can do that. And the similar workload paradigm of interactive workloads can be done with SLAs. So you could have a NoSQL store like HBase running on top of HDFS and have an application that has, like, let's say, 10 millisecond SLAs for gets and puts. Or search, or you have Impala queries running on the data in HDFS, and you have SLAs associated with that. So you could do that with HDFS. So, and with these two sort of storage systems, the predominant way of running a cluster with S3 is a transient cluster, where your cluster doesn't have any state. It is really something that you would provision to run some sort of a workload and then kill it after that. And with HDFS, you have a long-running cluster where the state is stored in HDFS, right? And so the role of your cluster in a transient cluster with S3 is only compute. With a long-running cluster with HDFS is compute and storage. The frameworks that you would run in a transient cluster they're predominantly either MapReduce or Spark, right? So that's really the batch frameworks that you would use. But on the other side, with long-running clusters, with HDFS, you can run those. You can run HBase, Solar, and Impala. So those are the two deployment models, right, out there that you have available in AWS. Let's dive a little deeper into different choices in terms of storage, and what are the access patterns and sort of performance implications of these different choices. Now, before we go into the different choices, I want to highlight a difference in paradigm with Hadoop and how cloud environments work. The Hadoop paradigm is you bring compute to storage. So you have data stored in disks on individual servers, and you ship your compute to as close to those disks as possible and minimize reading over the network. And that's the fundamental paradigm behind Hadoop. Whereas when you're running in cloud environments, that's not the paradigm that you run with. You consume everything as a service, including storage, and which is S3 in this case, right? So with S3, you're reading everything over the network to your EC2 instances, and there are certain performance implications of that. So these are two different paradigms with Hadoop and cloud, and this is where it gets interesting, because you trade off flexibility for performance and the kind of workloads that you would run. So let's look at the choices of storage in AWS. You have the instance stores, which is the ephemeral drives on the individual instances. They are really local disks attached to the instances, and different instances come with different amounts of local storage. They are temporary in nature, so if you shut down an instance or stop an instance, whatever's on your ephemeral drives is lost, right? They're also instance dependent. So you can't really say, I want this much storage on this particular instance. They come with whatever they come with, and you got to use that. That goes into EBS, which is you could attach additional volumes, and the life cycle of these is independent of the life cycle of the instance, right? But again, with EBS, everything is over the network. It's not local disks on the instance themselves. So there's performance implications of that. The third is obviously S3, which is really an external data store, right? So you have a very simplistic API. You get objects, you put objects, you delete objects. And the bandwidth to S3 is dependent on the instance that you're interacting with S3 from. let's talk about S3, and then I'll talk about running HDFS and what are the considerations there. You could interact with S3 from MapReduce jobs by using the S3A URI, which is available in the upstream Apache Hadoop project now, and that uses the native SDK. So you could do that and use S3 as a source or destination for your MapReduce jobs or Spark jobs, right? This CP is really a specialized MapReduce job under the hood, which basically copies data from one location to the other, and it could be from S3 to HDFS or vice versa. HBase has snapshots, and it has the ability to export snapshots straight to S3. And you could do that from the HBase command line and say, here's this particular snapshot name, I want to run these many mappers, copy it to this location in S3. And you restore from it later on. So those are the three things that you could do with S3 from a Hadoop deployment. And for backups, for example, you would use this CP. There are multiple implementations for interacting with S3 in the Hadoop project. So there's the S3 implementation, which is a block-based implementation, where Hadoop treats S3 as sort of a storage system where it would put the blocks of the file. So HDFS has files and then splits them into blocks, and it'll store the blocks in S3. Now, the downside of that implementation is that no other application can actually interact with the data because nobody knows how those blocks combine to form a file. So that metadata is still living with Hadoop. So that's not the most optimal implementation. S3N is a file-based implementation which uses JetSet under the hood, and that treats S3 as a file store where it'll store files. So the metadata is managed by S3. Any other application can come in and actually talk to S3 and get access to those files. It uses JetSet, which is, like I said, a third-party library, open source library. S3A is the latest one that has been written that uses the AWS SDK. And there's a bunch of optimizations there in terms of how it interacts with S3 that S3N doesn't have. So that's the latest one that was just committed a couple of months ago. And that's the one that we recommend you use. Now, the bandwidth to S3, like I said, is dependent on the instance, right? And the maximum that we have seen in our testing is about 200 megabytes a second. And that is not what Hadoop sees. That's what that's a raw bandwidth from the instance to S3. And 200 megabytes a second is with some of the larger instances. If you go to, let's say, the M1 family or an M1 large, that's not what you'll see. You'll see a much lower throughput there. So that's a consideration to keep in mind. So 200 megabytes a second, you're really looking at it as the equivalent of 2 local disks, right? So that's the max that you can get from an instance to S3. Now, like I said, Hadoop doesn't see that, and there's a reason for that. When you're moving data between HDFS and S3, what happens is, from HDFS, the data gets copied over to each file, would get copied over to the local file system, where a checksum is calculated, and the splits are calculated for multi-part uploads. That can't be done in HDFS itself, because HDFS doesn't have the ability to give you a checksum for an entire file. It'll give you checksums for blocks. So because of that, you have to copy it to the local file system. Now that's an overhead, and it takes time to do that, because of which you'll see the end-to-end throughput drops from 200 megabytes a second because you have to pay that cost. Now this is the second cost that you pay. You upload to S3 in a temporary space. You don't upload to S3 in the final location. You upload to S3 in a temporary space, and once the entire file is complete, you rename that file. Now in S3, a rename is equal to a move operation. So let's say you uploaded a 40 gig file. You'll now, to complete that upload, you have to wait for that file to get renamed or moved to its final location, right? It's not something that's going to happen in a couple of seconds. So you lose some time there. Both those things put together, you realistically sort of see a throughput of about 130 to 150 megabytes a second from the larger instances. Now, there's a bunch of tuning that you can do with S3 interactions from Hadoop. And there's a couple of things that when you're moving large files, you need to think about, and that's predominantly around task timeouts, and I'll talk about that. So tuning, the first thing that you want to do is parallelize as much as possible. Now, the throughput that a single thread will see to S3 is not 150 megabytes a second. That's not what you'll see from a single thread. But multiple threads combined from a single instance can get you 200 megabytes a second. So you want to parallelize as much as possible. Now, does that mean you run 4 tasks? Does that mean you run 8 tasks? That depends on your environment. That's something that you'll have to test and figure out what the optimal this thing for you is. We saw at about 10 tasks, we saw most of our experiments sort of max out at about 10 tasks. Going beyond that doesn't give you any additional benefit. So when you're writing to S3, there's multi-part uploads that is enabled, that you can enable in the S3 connector, and that's just a standard configuration that is there under the hood. But you want to enable it in the Hadoop configuration so the connector knows to run that. For the local staging directories, you want to use multiple drives, because otherwise, let's say, from a single node, you are uploading 5 10 gigabyte files, and all the tasks start to write to that single disk. You'll bottleneck there, and we saw that happen several times. So there's a patch upstream which allows you to specify multiple drives there, and it'll round robin between those. And that increases your throughput, of course. Up the task timeouts when you're writing large files. And what that means is when a task is writing to S3 and then it does the rename operation, S3 does not give you back any heartbeat or sort of status of that rename operation, right? It'll block there. And when it blocks there, the task is not getting any, it doesn't ping back the job tracker. So what happens is the job tracker after 10 minutes will say, I haven't heard back from this task, let me kill it. It's dead, right? And what would have happened is a 40 gigabyte file, which is pretty common when you're exporting HBase snapshots. 40 gigabyte file, at the end of the move operation, the task gets killed. So you want to up the task timeouts. The downside of upping the task timeouts is when there's genuinely a stuck task, it takes that much longer for the framework to figure it out. So what you want to do there is play with, the default is 10 minutes. You want to play with that setting and see what the optimal is for you. We upped it to about an hour for 40 gigabyte files. And that's when the job would complete reliably. Reading from S3, there's range reads that's built inside the S3 connector, which has multiple threads that read a single file. It does not split a single file to multiple map tasks. And the reason for that is there's no way for it to then combine those multiple parts back without the reducer understanding how the file works. And that is not something that has been built into the connector yet. Today, it's multiple threads within a single map task. Now, when working with S3, larger objects are better. So think a smaller number of large objects versus a large number of small objects. When you're doing large reads, or sort of saying, give me the entire bucket and I'm going to scan through it and run my aggregate, if you have too many small files, there's a load on the metadata server in S3 that'll cut your throughput down. So you want to have as many large files as possible and as low number of small files as possible. For the metadata lookups, you also want to randomize your file names. So that way, your load on the metadata service is spread out. Right? So that's the other thing. Now, Hadoop doesn't do that for you. You'll have to do that on your own. So which means if S3 is your landing zone for data that's coming into your data management framework, you want to randomize the names as much as possible. Now, oftentimes that's not possible, or it's just additional work. But that's the price that you would pay, is the metadata service being the bottleneck. So that's about S3. Let's talk about how do you run HDFS. So you want to use the ephemeral drives in EC2. And it's OK to use the ephemeral drives because Hadoop has replication under the hood. And if you lose an instance or you lose a couple of instances, you won't lose data. So Hadoop will take care of that from its replication standpoint. So it's OK to use the ephemeral drives there. Now, it does not give you the same level of durability and reliability as S3 would. But at the same time, it gives you a fairly high durability. And it's obviously, HDFS will be persistent for as long as the instances are alive. You can't pause an HDFS instance, because the moment you stop the instances, you lose the data. And you want to use S3 for backups as much as possible. Now, we don't recommend you use EBS to back HDFS. And the reason for that is everything is going over the network at that point in time, right? And EBS is really designed for random I/O. Now, as of this morning, with the new numbers that EBS can support, up to 160 megabytes a second per volume, some of this is up for consideration again. And we'll be looking into where EBS can fit in. But as it stands today, EBS is sort of an anti-pattern. Let's talk about networking. So so we recommend deploying in a VPC, and the reason for that is it looks like an extension to your data center. And with VPN or Direct Connect, that's what you can configure it to be. But if you're deploying in EC2 Classic, everything, so the only way to access stuff there would be over the public internet. And you don't want your Hadoop cluster to be, the only way you can access it is by going over the public internet. So we recommend you deploy in a VPC. In a VPC, you can have two kinds of subnets. One is a subnet where all your instances have the ability to interact with things outside the AWS network or sort of over the internet. S3 actually happens to be something that you need to go over the public internet pipe to interact with from EC2. So if your instances or if your Hadoop cluster needs to interact with S3, for example, for backups, or S3 is your landing zone, which is what we recommend that you do, you need to have your data nodes be deployed in the public subnet so that it has full throughput to S3. And on your corporate network side, you can set up a VPN or Direct Connect so that you have the ability to interact with the EC2 instances without having to go through the internet. The other deployment model is where a cluster is set up in a private subnet. And a private subnet is where these instances don't have the ability to interact with anything outside AWS, as outside EC2. And the way you would do that is, if you needed to access anything over the internet, is by going through a NAT instance that you would set up in a public subnet. Now, that is not the way you would want to interact with S3, though, because you'll be bottlenecked by the throughput that instance can serve. So for a large cluster, you'll choke that pretty soon. So those are the two deployment options or topologies when deploying inside VPC. Then there are performance considerations from a networking standpoint. The instance-to-instance link is important because you have replication happening in HDFS. MapReduce jobs have shuffles and sort of sort phases. So do Spark jobs, and you need a good network at that point. Some instances come with 10 gig. Some instances come with 10 gig with enhanced networking, and you have to use the HVM AMIs for that. And there are other instances that don't have a 10 gig link. Excuse me. They have low, medium, or high network, and that does have performance implications. So we'd recommend using the ones with 10 gig or 10 gig plus SRIOV as much as possible. The instance to S3 is equal to the instance to public internet link, and again is instance specific, and that is something that you get with the 10 gig. The instances that have a 10 gig link have a higher throughput. It goes up to 200 megabytes a second, like I said. Placement groups is something that is important to consider here. When you deploy instances inside a placement group, AWS tries to give you instances as close to each other as possible. And they also guarantee that the instance-to-instance bandwidth inside a placement group would be a full 10 gig link. However, if you're not, now the downside of deploying inside a placement group is that you have a limited pool of resources from which you'll provision. If you're not deploying inside a placement group, you could run into situations where instance-to-instance link would drop to something like 2 gigs, and that's what we saw in our testing. And you don't want that in a large cluster because then your performance is not predictable. Because sometimes your writes would take longer because you're going through that 2 gig pipeline. And so we'd recommend deploy your cluster inside a placement group. And also inside a single availability zone, right? So we don't recommend you deploy clusters across availability zones. Now, having said that, that is sort of an anti-pattern when it comes to deploying in AWS, because going across AZs is the recommended way for high availability. As it stands today, Hadoop can't really leverage that very well. And you'll see a significant performance drop when you're going cross AZ. Let's talk about the different EC2 instances. So there's transient clusters. The primary consideration for picking instance types are bandwidth, CPU, and memory, right? And bandwidth is to S3 that you care about. And it's more the aggregate bandwidth across the entire cluster than the bandwidth from a single instance. CPU and memory are obviously important depending on whatever workload you're running. So there's no, I wouldn't say there's a magic number that you need to work with for CPU and memory. Availability and fault tolerance for those instances is not that important because if a cluster dies, you're fine, you can just provision a new one. It's really stateless. It doesn't hold any state except that particular job. So from that perspective, it is important, but otherwise it's not the primary consideration. Similarly, local storage density is not a primary consideration for transient clusters. Typical instance choices that we see customers choose for that workload, C3, M3, M1 families. It's really an anti-pattern to use something like an HS1 or a CC2 8XL for a transient cluster. Long-running clusters, on the other hand, local storage is really the key, right? And you want to plan your cluster and choose your instances based on how much storage you need. CPU memory obviously are important from the workload standpoint. Availability and fault tolerance becomes important here because that's where your state is stored and you want the cluster to be as available as possible. Now, some of the larger instances have smaller number of virtual machines per physical host than some of the smaller ones. And so using the larger ones for long-running clusters makes sense. Also, you'll get a higher bandwidth in those ones. So otherwise, if you use the smaller instances, the instance-to-instance network is smaller. Typical choices that we see customers use, HS1 8XL large, CC2 8XL large, I2 8XL large. Mostly for storage-heavy use cases, HS1 8XL large is the instance type that our customers pick. From there, you obviously have to pick the right AMIs as well. You really have two choices, right? So there's either PV or HBM. And one thing that I would say is pick a dependable base AMI, something that a vendor supports, because you don't want to be worrying about and managing your own AMIs. And so if somebody supports an AMI, that would be the place that I would start. Things to look out for when you're looking at an AMI are the kernel patches up to date, are all sort of the third-party software and library versions up to date based on whatever you need to run. Those are the things that I would say look out for. And you know, when I say a dependable base AMI, what I really mean there is like people like you and I can actually go and create our own AMIs, put it in the marketplace. Try not to use those. Try to use the ones that Amazon is providing or Red Hat is providing. One of the things with any AMI that you might choose is increase the root volume size. The default root volume is actually pretty small, and you'll very quickly find yourself in a place where logs would fill it up or packages would fill it up. So we recommend going to at least a 500 gig root volume for a production deployment. Let's talk about security. Now, you want to deploy in VPC, so we talked about that, right? And you have two choices there, private subnets or public subnets. And it becomes important to look at how you would secure this environment. Network ACLs at a subnet level are available where you can block certain kinds of traffic to a certain IP range, right? Or all inbound traffic from anything outside EC2. Or the internet, right? So you can block those things at the network ACL level. Security groups is something that I would say you should spend more time on security groups rather than network ACLs, because network ACLs are stateless, right? The security groups they're stateful and give you more flexibility in terms of how you define your rules. And allowing for traffic, sort of inbound traffic from your subnet to your data center, probably not a good idea, right? Unless you really need to be able to push something from the cluster down to your data center. But the other way around is important, especially if your cluster is in a public subnet, right? So you're accessing S3. So work with I would say, the IT team on figuring out exactly what rules you need to abide by from a security standpoint. But those are the things that you need to be careful of. Beyond that, there is nothing AWS specific that you need to do. There's nothing Hadoop specific that you need to do from an AWS deployment standpoint. It's really thinking about security groups and ACLs and your subnets that is just sort of structuring it in AWS. For Hadoop, the standard guidelines around Kerberos, AD integration, encryption, those exist just as much in AWS as they would in on-prem deployments. So there's nothing special there. Now, for backups, obviously, S3 provides server-side encryption, so that's the other security consideration, and our customers use that pretty heavily. Let's look at HA, backups and disaster recovery. Now, HA is available in the Hadoop stack, right? So you run multiple name nodes, you run journal nodes to manage your edits, you run multiple zookeepers if you're running anything with Zookeeper, you run multiple HFS masters. That's just available in the Hadoop stack, and you use it just as is. Again, nothing AWS specific there. Backups and disaster recovery are a little more interesting because when you're doing on-prem deployments, the only way you do this is you have another HDFS cluster, right? So that's the only choice from a backup or a DR standpoint. Or you would use an expensive shared storage. But in AWS, you have the ability to use S3 for a warm backup. So I would say that is something that you should absolutely do. For a hot backup, though, running multiple clusters across 2 availability zones is something that our customers consider in that particular use case where they need a hot backup. Warm backups, S3, and Glacier is obviously available for cold backups. We don't really see that being used a whole lot. So let's look at sort of planning your cluster, right? And we talked about all these different considerations from storage, compute, networking standpoint, but really, how do you go about using all of this and planning your first deployment? The bad news is there's no simple answer, unfortunately, right? You have to think through all these considerations. Now, the good news there is mistakes are really cheap, right? You don't like what you see from a performance standpoint, kill the cluster, get a new one with beefier boxes. And obviously, whatever we're sharing here is what we've learned over the course of the last year and a half supporting production deployments in AWS. So what you want to start with is, what is the workload type that you care about? Is it an ad hoc or an SLA workload? Is it batch? If it's purely batch, then S3 is obviously a good choice. But if you need the interactive workload with Impala or HBase or Solar, S3 is not the storage system that you would want to work with. So that's the first place that you want to start. From there, what percentage of the day would you use that cluster for? So if you're going to use it only for 4 hours and for a batch workload, a transient cluster makes perfect sense, right? But if you're going to use it for more than 20 hours a day, you don't want to pay the price of spinning it up, spinning it down, or hydrating it with data. You're probably better off running it with a long-running cluster. How much data are you storing? And that would impact the instance types that you would pick, right? Because different instance types have different amount of local storage on them. And what are your performance requirements? So the CPU and sort of memory and bandwidth are things that you will have to think about from that standpoint. How you're ingesting your data and what the workflow looks like is also important. So do you have Flume? Do you have Scoop? Are you bringing it in from a database into Hadoop? And that way you need a long-running cluster that's doing that ingest continuously. So that's an important consideration. And what does your workflow look like after the data lands? Like, does it get cleansed and is it then consumed? Going back to what the workload type is at that point in time. So those are the things that you want to think through as you're planning your cluster. To make your life easy, we have a product called Cloudera Director, which just provisions. It's really a provisioning tool at the moment, and it automates the entire provisioning process. So you don't have to worry about setting up the different daemons. You don't have to worry about setting the MI and things like that. All that you do is tell it the instance types that you want, the size of the cluster, and it'll give you a cluster back. And this was released about a month ago. You can consume that using the AWS Quick Start, and it'll set up your entire VPC using CloudFormation. It'll set up Cloudera Director and have a running cluster for you at the end of that cycle. There's a reference architecture that we just refreshed that talks about all these considerations, that talks about subnets in more detail. It talks about the different instance types that you can pick for different workloads. And then there's that's available on our website. And then there's a best practices blog as well, which talks about, again, a lot of these considerations that we just talked about and goes into some detail. So those are the things that are available to make your life easy. That's what I got. Thank you.